Hello, welcome. Today we discuss on SIRS epidemic model. Susceptible, infected, recover, and again susceptible. This type of model. This is the question from 2022 University of Calcutta. Consider the compartmental model dSdt equal to this, didt equal to this, drdt equal to this, where the parameters lambda, mu, alpha are all positive, are to be explained by u, and S0, I0, R0 are initial values of the susceptible, infected, and recovered populations respectively, so that at any time t, the total number of population is constant. Number two, reduce the system into two-dimensional system involving S and I population only. Number three, calculate the basic reproduction R0 and show that the epidemic can grow if R0 greater than 1. Number 4, discuss the stability of each equilibria of the reduced system. There are three equations. This dsdt, the rate of increment of the susceptible, dsdt is this. So dsdt is this from S, dsdt from S is minus lambda si. So this is the lambda is the disease transmission coefficient from susceptible to infected. So this is the lambda si. So this is the negative sign. And input this susceptible is alpha r, which is from r, recovered from r. So this is the plus alpha r. So this is the input to S. Output from S is lambda si. And the mu is the recovery rate from infected to R. So did equal to this is the plus lambda si. This is the input of this to this, and the output is mu I, recovery rate from the infected. So this is the minus mu I, and alpha is the rate at which the immunity is lost. So for drdt equal to plus mu I, and this the output is the alpha r. So minus alpha r. Adding the given three equations, we get dsdt plus drdt plus drdt. This we get this equal to 0. So s plus I plus r equal to constant. Initially, at time t equal to 0, let s equal to s0, I equal to I0, r equal to r0. Then s plus I plus r equal to s0 plus I0 plus r0 equal to capital N is the total population of this. Hence, at any time t, the total population is always constant. Next, from 4, this r equal to n minus s minus I. So from 1, equation 1, dsdt equal to minus lambda si plus alpha r. We remove this r by using r equal to n minus s minus I. So put this, and from the second equation, did equal to lambda si minus mu I. So there is no r here. So we get two-dimensional system, this involving s and I. Now we solve this. We can solve this for this s and I. Now we are interested for equilibrium points and their stability. So for equilibria, we must have dsd equal to 0, and dIdt equal to 0. Then obviously we get this equals to 0 and this equals to 0. And from 7, taking common I, so I equal to 0, either I equal to 0 or lambda s minus mu equal to 0, that is s equal to mu by lambda. When I equal to 0, put I equal to 0 in 6, so we get this equation. So s equals to n. Put I equal to 0, we get n minus s, so s equal to n. So we get this the equilibrium E0, equilibrium point E0 equals to n comma 0, n comma 0. First equilibrium point is this equilibrium point. When s equals to lambda by mu, from equation this 4, no, this is the 6, from 6 we get lambda into mu by lambda into I plus alpha into n mu s equal to mu by lambda minus I. So we get, after simplification, I equal to this. So here s equals to mu by lambda is called a star, and this I equal to this, so called it I star. So we get endemic equilibrium point E star equal to A star comma I star, where A star is this and I star is this. Now for existence of E star, obviously A star is positive and I star is positive. Obviously A star is positive because mu and lambda are both positive. So I star is positive when n lambda by mu minus 1 is greater than 0. That is, n lambda by mu is greater than 1. That is, R0 is greater than 1. We call this R0 equal to n lambda by mu is called basic reproduction number. So when R0 is greater than 1, then the endemic equilibrium point E star exists. Now the stability test for this equilibrium, let f is a function of Si is equal to minus lambda Si plus alpha bracket n minus S minus I, and GSI equals to lambda Si minus mu I. So del f del s, del f del I, del g del s, del g del I, and we get Jacobian for the system. Del f del x, del f del I, del g del s, del g del I, we get this. Now from 2, dIdt is positive if lambda s minus mu into I greater than 0. That is, if this greater than 0, this I is obviously greater than 0. So R0 is greater than 0. Initially when t equal to 0, this I equal to 0 and R equal to 0. So n is approximately equal to s. Total number of population is equal to the susceptible at t equal to 0. So epidemic can grow if R0 is greater than 1. When R0 greater than 1, dIdt is positive because dIdt is positive. If R0 greater than 1, then epidemic can grow this. And for the disease equilibrium point D0, we get J at the point D0. This is the value. Put this put for n equal to s equal to n and I equal to 0 in this matrix. So we get this. This is the upper triangular matrix. So its eigenvalue are minus alpha, lambda, and minus mu. Alpha is positive, so minus alpha is negative, and this lambda n minus mu is negative if lambda n minus mu is less than 0. So if taking common mu, so lambda n by mu minus 1 is less than 0, that is lambda n by mu is less than 1 because mu is positive. So if R0 is less than 1, then this eigenvalue lambda n minus mu is positive. So both eigenvalue are negative. So both eigenvalue are negative, hence this E0, this equilibrium, is locally asymptotically stable equilibrium if R0 is less than 1, and if R0 greater than 1, it is unstable equilibrium. And then the endemic equilibrium star exists. Now J star, this equals to this, put star equal to mu by lambda, I star equal to alpha mu by lambda bracket alpha plus mu bracket R0 minus 1, and so we get for star, we get this matrix 2 by 2 matrix. The trace of this J star is the principal diagonal elements, sum of the principal diagonal elements. So this equals to this. So obviously this is negative because R0 is greater than 1. So R0 minus 1 is positive. So this is positive, or positive is positive. So it is negative. And determinant of this J star, obviously this into this minus this into this. So obviously this R0 minus 1 is positive are all positive. So this is positive. So the endemic equilibrium star will be locally asymptotically stable if R0 is greater than 1. Thank you for watching this video.